So this is not a misprint, and this is work I've been doing over the last 6 years or so with Louis Pierre Argan, who is now going to be in New York, and Nicolas Kistler, who is going to be in Frankfurt, and in the last year and a half with Lisa Hartung, who is a PhD student of mine. So we will talk about, I will introduce first a general class of Gaussian processes on trees that I'm interested in, and then I will specialize to the classical object of branching Brownian motion, of which the great hero, Murray Branson, happens to be in the audience, so this is a particular honor for me to speak in his presence. And then I will tell you about some older and newer results in this domain. But let me start, sorry, no, this is terrible.
F5.
What F5? Okay. So let me start with some motivations for this talk. There are actually four. And the first one is about spin glass, and people that know me will not be surprised. So you have a question that would be, what is the structure of ground states of, let's say, mean field spin glasses? You know, this is a question which is interesting in statistical mechanics. Another question which is maybe more interesting for a general probabilistic audience is extreme value theory. So you have extreme values of stochastic sequences of processes or fields. What is in particular what happens in the dependent cases. We know there are results, but this is not a really completely well understood subject. The other thing is about spatial branching processes, right? You know, branching Brownian motion is the classical spatial branching process. You could be interested in that from reasons of biology or whatever. And then there's a relation to nonlinear PDEs, reaction diffusion equation, convergence of solutions of those which happen to be related, as we will see. So you can pick any of these motivations, and if you don't find any of that interesting, you might still use the opportunity to go. I mean, now, this is of course in general quite hard. I mean, these questions, and so we will actually focus on this in a setting where there's a chance to answer this, and branching Brownian motion is in the center of this setting. So the setting is Gaussian processes labeled by tree. So what I mean by this is follows. You start with a tree, time homogeneous tree, where you label individuals, you know, just number them at time t, I1 to up to int. You always assume that these trees don't die out, and they can be random or it can be deterministic, and that they grow exponentially, as we will see. So, and then there's a, you know, with the tree, you have the canonical tree distance, which we will just take the time of a recent most common ancestor. So you take two individuals, you go back along the tree, and then they have a recent common ancestor at some time, and this we will denote by the distance. It's not really a distance, but we will call it a distance anyway. Right? And given that, you can, for a fixed time horizon, define a Gaussian process given the tree. So you give yourself this tree, and then you, oops, now I'll make this too fast, so it's here. And there you just say, well, we take on each point on the tree up to time t, you know, that we go back at some time s and some individual k, you declare that these have covariance given by a function of this distance, v, and then you have to sort of rescale it properly to normalize it so that we have at the end variance t. And A here, this is the key object. A can be chosen as any non-decreasing function from 0,1 to 0,1. And that gives you a class of processes that will range from ID random variable to totally correlated random variables. And in fact, this sort of nice observation is that these processes actually exist, and they can all be constructed as time change of branching Brownian motion, in the sense that you fix your tree, when you run along the timelines of this tree a Brownian motion with a desired speed, which is basically given by this function a here, and then you branch, whenever you hit the vertex, you just branch into independent ones. Right? So this you can do for all of these things, and so these processes exist. And what we will be interested in, well, let me just start with examples that I put up. So what are the examples that belong? So the first thing is what trees could you use? Now the simplest tree, you could use a binary tree, right? So here's a binary tree. And then if you choose your function a of x to be just the identity function, a of x equal to x, then you get branching random walk. You know, it goes back to Harris, I guess, or even earlier, in 63. If you take a step function, and we come to that example later, you get what is called in physics the generalized random energy model. It was introduced by Derrida and Gardner in 82. So this is just for those who know. I mean, otherwise I will say something. Now, the special case of this step function is, of course, a function which makes just a single step, so it says 0 up to 1, and then at 1 it jumps up to 1, and that you get what is called in physics the random energy model, but which is just IID random variable. Then you have just n of t, you know, the number of leaves at time t of the tree, IID standard Gaussian random variables are with variance t. Okay, so this is the simplest thing, everybody understands. And if you take a continuous function, or maybe not necessarily just a step function, we used to call this the crème, but it was introduced also by Derrida and Gardner. Defined it, I mean, we looked at this in 10 years ago with Irina Kurkova. Now, the other case of the tree is the Gordon-Watson tree, right? So it's a continuous time tree, so it looks a little bit more fancy. So we just split at exponential times with respect to some distribution, and we will always choose this distribution in such a way that the tree doesn't die out. And then if you take a of x is equal to x, what you get is exactly the classical model of branching Brownian motion. And if you take a general A, then what you get is what we will call it now variable speed branching Brownian motion. This has been introduced by Derrida and Spohn in 88 and recently been studied by Fang and Saitumi in the last couple of days. So what happens now? So now we come to extreme value. So what are the questions? We have 3 questions usually that you want to ask in this context. So the first one is, how big is the maximum? Just to take the maximum of all these xt's at time t, and then you sort of divide it by t for good measure, and you can ask, is this converging to something? So this is a law of large numbers type of result. Now, the rough idea how large these maxima of these processes are. Then you can ask a more subtle question, which is what is there a rescaling when you find a function ut of x such that, you know, the probability that mt is less than ut of x converges to some nice function. Also, this is also a classical question. Also, that's the next one. So, is there an extremal distribution, as a rescaled maximum has some nice distribution? And then there is the question, we can now look down, how do these, not just the maximum, but the large particles of this process, how do they look? So you can basically say, well, can I rescale? So you take this xt of x's, you scale them back by the inverse of this function u, if that function exists. You plot the points. You ask, is this going to have some limit? You know, stochastically, is some object that we can describe? Is it point process or whatever? So these are the 3 questions. Now, just for reference, in the case of a random energy model, which is for case IID random variables, in this case n of t IID random variables, this is of course classically known, and I just recall what is known. Right? So m of t over t converges to twice the growth rate of a tree. That's just the law of large numbers. So r is the growth rate of a tree. This thing here will exist. And the rescaling function, you can actually choose it in this way. It looks a little bit complicated. I wrote it deliberately as such. So the rescaling function is affine, and you have this first party, which is t times square root of 2r. Then there's a logarithmic correction, which is deterministic. This comes from the growth rate. Then there's the x divided by square root of r. So this is just the shift. So basically, right, this is the order, the more precise order of the maximum, and then this will be a random variable. But there's a random part. Actually, it's not, you know, it's an nt, you know, you choose this, which is the logarithm of nt over this expectation divided by the square root of 2r, and this nt over e of t converges in general to a random variable. It could converge to 1, you know, in the case of a binary tree, it's just 1, that's also a nice number. The logarithm of 1 is 0, it's even nicer. But in the case of a Gordon-Watson tree, for instance, this random variable is an exponential random variable of parameter 1, which is well known. So this is in general like this. And then you get the law of a maximum is given by this, if you rescale like this, by this Gumbel distribution. Right? And just to make a little remark, of course, here I choose to make this rescaling function random in the sense that it has this random variable. You can of course drop this, and then it will pop up here as a random variable, and you get the expectation of that random variable. This we will see later. And there are two ways of writing this, and I will remark this also later. So this is one thing. And then the next thing is, which is also well known, if you now do this point process of extremes, you get the convergence to a Poisson point process. And this is what you learn in probability classes when you need to do something about extremely. And so this is just a thing. And now the question is, what happens to the answers to these questions when you take not, and this is for the function a, which is 0 all the time and jumps to 1. Right? So for IID case, and what happens to the answer to these questions in the general case? This is basically the issue that we have to solve. Is that all clear? So the first, there's universality in this picture, and when we have full understanding of universality is with respect to the question number 1, the law of large numbers. Now, if you just want to know what is the order of a maximum, then there's actually a complete answer to this question, and this answer depends only on the concave hull of a function a, and it's given by this formula. So there's you see, you have here again the growth rate, so this is twice, so m of t over t converges to square root of 2 times the growth rate of the tree, and then there's this funny function which is this integral over the derivative of a convex hull, etc. And so we proved this one probably proved in the Irina Kurkova in 2001 for the binary tree, and this, but I'm not quite sure that it's actually in their paper, but anyway, it's proven fun in Saituni in the case of the Gordon-Watson tree. And you see here, of course, that this term disappears, and it's just equal to 1 if the convex hull is just a linear function, right? So if whenever the function a stays just below the linear function when it's convex hull, it's going to be the straight line, and this term doesn't appear. So it only appears if a function becomes strictly concave. Yeah, that's what I just said here. And so this order of a maximum changes only if the covariance becomes strong enough so that you cross this line. Now, the other things that are known are in the case of the grams. The grams correspond to the case where the function a is a step function with finitely many steps. Right? So it's just like a distribution function of a disk of a finite random variable with finitely many values. And in that case, we know everything for a long time. So more or less. So if a of s is strictly less than s in that case, then everything is just like in the IID case. So you don't see anything on these all the three answers, like all the three questions I gave you. Everything is as if we were in this random case. If we have equality to a finite number, there are a finite number of points touch this straight line, right? So that it's not strictly convex, strictly below, right? But then you get still the same answer, but you pick up a prefactor, a constant. Right? So there's a slight thinning out of the extremal process takes place, and that was something we found also already 10 years ago. And while if a of s if the convex hull is not equal to the straight line, but you have still a step function, then you can actually construct the extremal process as a, by just sticking together Poisson process, point process. So basically what you do is you look at the little pieces where the a, the a is a step function, so each step looks like a random energy model function, or like a function that is constant and then jumps, and for this you already know the answer, and then it just turns out you have to just stick these processes together, you get a cascade of Poisson processes, and then you just sum these things up, and that gives you the extremal process. And you see here that REM is some of the building block to understand all the grams. This is a message I want to pass at this stage. So, but when this was known, but the extension, so as I said, so this was done for binary trees, and but for general trees, this is completely straightforward to do the same thing. There's no issue whatsoever. You see, again, the special case is the function a of s is equal to s. We cannot really, where something strange starts to happen, and we cannot really, or at least when we looked at this 10 years ago, we didn't really know how to handle the case a of s is equal to s. And then Erwin Bolthausen pointed out to me that I should look at these papers by Murray Bramson on the branching Brownian motion, because the case a of s that is that a of s equal to s, this sort of critical line where things start to kick in, this was exactly the branching Brownian motion as I pointed out. Now, branching Brownian motion, of course, is an object that was studied much longer from different contexts. It's a classical object, but the most classical object in population dynamics. The simplest way you can describe it, like Sylvie Milliard was explaining very complicated models of evolution, but this is a stupid model of evolution that things just branch, just reproduce, and then they keep growing, and then they move around in space for fun. That's what we have. Now, so here this looks like this, and so this is a canonical process, and it was of course studied, and we can ask of course the same questions. Now, what is particularly nice, and now we come to the first point of motivation, is that this process is also related to an equation from population dynamics, namely the Fischer-Kolmogorov-Petrovsky-Piskunov equation. I never could find a picture of Piskunov, so Piskunov is missing on this little gallery. And this is just an equation of that type. There you have a diffusion equation, a space-time diffusion equation, plus a nonlinearity. And this nonlinearity, I just wrote the simplest nonlinearity, which corresponds to binary branching, but in general, this term here, this v squared, should be the law of the branching law of the process. But this doesn't matter, it's all more or less the same. So this is this equation, and this equation comes from the evolution of biological populations, where you have birth, death, v squared is a negative term, and diffusive migration. And so it's quite interesting what's the connection, because here you have an equation for a population with self-interaction, whereas the branching Brownian motion didn't have any self-interaction. There's no interaction, it's a purely free motion. But the great thing is the connection between this equation and branching Brownian motion. This is a theorem which is usually attributed to McKean, but I have recently been told that it's actually, and it's true, it goes actually back a little bit earlier to these Japanese gentlemen, that tells you that the solutions of this previous equation can actually be obtained as an expectation with respect to branching Brownian motion in this form. So you have if you have this object, you take a certain function, you plug in x minus this stuff, take the product of all the points of the branching Brownian motion, take the expectation, you get u, and then 1 minus u will be a solution of the previous equation with initial conditions 1 minus f. There's always an annoying thing about these 1 minus things, because sometimes this depends on how you write the nonlinearity. So you have for u and 1 minus u, we solve essentially the same equation, but there's a slight change in sign at some point. So that's why this looks a little bit like that. So that's a nice way to write it for the u, but it's not a nice way to write it for the equation. Okay, so that was nice. You have a representation, and you could use this if you knew something about either the branching Brownian motion or about this equation. And then comes this amazing work by Murray Bramson in his thesis, where he proves, he will probably tell me that this is a paraphrasing of what he proved. So he proves two things. First of all, there is a stationary version of this equation. It's an ordinary ODE where the time derivative is replaced by a space derivative and the square root of 2. The square root of 2 must not be square root of 2, but for our case we are interested only in the case when there's a square root of 2. So you have this equation, and he shows that this is a unique solution that stays between 0 and 1, and that goes to 0 as x goes to plus infinity, and 1 as x goes to minus infinity, up to translation. So of course you can always translate this thing, you still get an equation, a solution. And then under suitable conditions on the initial conditions, which I will not write here because there's not enough time, but for certain classes of initial conditions, you find that there's a traveling wave solution, so there's a function m of t, and m of t in that case will be square root of 2t minus 3 over square root of 2 times 2 log t, and then this will converge to a solution of this equation. Right? And now, of course, the point is that with the right choice of initial conditions, you can produce probabilistically interesting functions for the branching Brownian motion. So, for instance, if you take for f the indicator function, from the Heaviside function, then you will find, the expectation of the product of this Heaviside function is just the probability that all the BBM is below this x, right? So then you can actually construct the probability that the maximum is less than x. Right? So the three previous theorem will give us immediately something about the behavior of u. And then there is also the case of the Laplace functionals. They also have in principle this form. There's a slight issue here that needs a little bit more work because we don't have the right behavior at infinity. But that is actually not, turns out to be not so important. And then, of course, this gave this celebrated result that Clemson got, that that gave us a u of t in the case of branching Brownian motion. And mind you that this m of t looks, go back, this m of t looks very much like the u of t that we had for the rem. And the main difference is that here, in the rem, there would be a 1 here instead of a 3. So it's almost like it. And of course, the omega of x here, that is now clearly seen not to be the Gumbel distribution because, well, the Gumbel distribution wouldn't solve this equation. But anyway, so this was this result. And then there's a nice paper which I also like very much by Lawley and Selke, where they actually give an interpretation, a probabilistic interpretation for this omega, sorry, I always move too fast here, of this omega in terms of, which looks like this, they say that all the solutions in that class that we're interested in, they look like this. They are essentially like a Gumbel distribution, e2 minus x, there's a square root of 2, and then there is two things, there's a constant c and a random variable z. Now the random variable shouldn't surprise us too much that there is a random variable, because I told you already in the random energy model, if a tree was a Gordon-Watson tree, there appeared some exponential random variable. But the point is that this z is not an exponential random variable, but it is actually what is called a derivative martingale, which is the limit of this object, which happens to be a martingale, and which one can prove converges to a non-trivial random variable. And so this is somehow telling us something about, and there are two things that are really crucial here. It says z and the c. Right? And the c is, this is the only thing that, basically from Bramson's result, that nothing else could happen. And once you have this form, the only thing that, whatever initial conditions you put, you can only get a different c. Right? So that's the only thing. So that was the result that says, well, in this case of a linear function, things are already different. And then, so now, strange enough, when for a long time this third question was not answered about the extremal process, and so that is what I thought would be important, in order to understand this generalized, this obvious process that we had. It would be important to understand that this borderline case for branching Brownian motion, understand what would be the extremal process, which you can easily convince yourself cannot be a Poisson process, right? So I will now start by giving you a description of this process, and then I will make, what of a process, which we will then see is actually this limiting process. So the way this goes is as follows. We start with, we take this z. Remember, z was this limit of the derivative martingale, so it's a random variable, right? And then we have we take a Poisson point process with this random intensity z times c times e to minus square root of 2x. Okay, so this is just the Poisson process. So this is one ingredient, and then we need another ingredient which we call the cluster process, which is done as follows. You take a branching Brownian motion, and now you plot the points minus the maximal point. Right? So that means in particular that you put all the x k's of t and subtract the maximum. So you always that at 0 there is a point, and then all the other points are negative. Right? So this is how this looks like. But then you don't take an ordinary branching Brownian motion, but you condition it to have a maximum which is larger than square root of 2t. Now it only wants to be square root of 2t minus 3 over 2 square root of 2 logarithm of t. So this event has probability 0 asymptotically as t goes to infinity. But never mind, you condition on that. Right? And this, interestingly, when we looked at this, is something, this type of process, I mean, a branching Brownian motion condition to do things which are much worse, I mean, than they actually want to do, was already studied in Chauvin rule in about 1990. So the nice thing was we could take from them that this process actually exists, right? And then what we do is, once you have such a process, so wait a second, so they should, yeah, you take the limit, yeah, so the limit as t goes to infinity of this process, so it looks somehow like that here, just a picture, it has this point at 0, and then there's basically this drifted Brownian motion that goes down here, and then there are little branches that start off, and they cannot go higher than this red one, so this is a description of that thing. And now you take IID copies of it, right? You just take IID copies of this, and then what you do, you construct a process E, which is just giving you sum over all the points of a Poisson process over here. You add, then you add to that with all the points of one of the copies of this delta process, and then you just sum over all these points, and it gives you a point process. And then the statement is that the point process of extreme, so you take the delta xi of t minus this m of t that was in the maximum, then this converges to this process E. And this has been proven about 2000, well, it was in 11 in 2 papers by Arnaud, myself, and Kistler, and by Julien Beresticki, who is here, is not the other one, and Schill, and sort of more or less at the same time. There's somehow a different twist to the proof, which I may comment on also maybe a little bit later. So the picture and the interpretation, so that this always follows. So you see you have this is somehow this branching Brownian motion. Here you look at the top, and what we say is, well, why is that like this? So the first thing is, where is this derivative martingale coming from? This Z. Why is there randomness in the intensity of a Poisson point process? Well, it's like in the REM. There's just at the beginning, something happens, and either the process branches or it doesn't branch, and that's if you didn't branch when you're very young, I mean, you lose this forever. So there's, right, I mean, if you didn't grow, I mean, the first year of your life, right, I mean, then you're just smaller than, up your age. You don't recover from this. But after some relatively short time, this averages out. So this is a random variable which is measured with respect to f infinity. So it's not a tail random variable. So this is really nice martingale limit. And at that time, of course, also, your children, at a very short time branch off, so there's a very short time that people branch off. And then you just go up, and then here on top, of course, you see again, this cannot be the end of the story. So what one first can show is that the maxima of all these little clusters here, so these points pi, they actually can be interpreted as the maxima of groups of particles which had relatively recently a common ancestor. Right? Because then, if you are very big and you had, a child just a minute ago, it's not going to have run away very far. I mean, so it stays next to you. So if you see somebody who is very large, then there will be somebody some relative which is also there. And this can also not be avoided. And this is why there has to be some process like this delta process. Right? This is just what it is. So this is why we, in a way, it makes a lot of sense. And as you will see, in order to prove this result, you have to somehow understand this before you can actually really prove it. And I will tell you sort of why. So I will tell you how we prove this result. So this is the Arnaud and I paper. So we go through Laplace functions. Now that's a natural thing. You have a point process. You want it to converge. So you take some class of functions that determine convergence. So Laplace functions, as I already said, they look nice in the sense that they give you have a representation in terms of solutions of the FKTP equation. And so what we did is we just prove that this, we take e to minus some positive continuous bounded support function, integrated again. So this Laplace function of this process for function phi converges to, well, the same thing as in this thing. It converges to e2 minus a constant times this z. This z is again this derivative martingale, and this constant depends on the phi. This is the only way how this answer can depend on the phi. In fact, you can show there's a representation of this in terms of a the solution of the FKPP equation with the initial condition e2 minus phi of y. Right? So you look at this thing and say, well, you know, that's great. What do we do with it? Right? You say, well, that proves that it converges. You know, well, you have to prove that the C is not 0 or infinity or 0, so and so on and so forth. That is not real, but this you have to do. But then you get an answer, but you don't understand the answer, right? Because it doesn't tell you anything about what the process is, but unless you already know what the answer should be, right? And then you take the process that we have just constructed, the E process, and you compute its Laplace function. Right? And then you show that they are the same. Right? So that's what basically happens. So you just show that this answer that you get is exactly the Laplace functional for the process that you have, and then you know it. But if you hadn't sort of known what to look for, I mean, you would not never have guessed, I guess, from this sort of relatively abstract representation. So this is how this goes. So how am I doing in time? 10. Okay, so let me now come to the more, so this was, as I said, 2011. Now let me come quickly to the more general case. So we try to look at the case of this variable speed branching Brownian motion, so where we have a function a, not the straight line, but some other function, right? And let me just first, we want to look at the case where this function a lies below the straight line, yeah, and the slopes are also here less than 1, and the slope here also larger than 1. So this is the first case, and here we have the result of the last 2 years that says the following. So now suppose you take such a function, you call the slope at 0 a squared and the slope at 1 b squared, and then there exists constants c of b, so a constant c that depends only on the slope at one end, and a random variable y that depends only on the slope at here, such that, well, you know, the probability that the maximum minus m tilde t, not the mt from the Ramson's mt, so the mt from the Ram, so the mt with a 1 over 2 square root of 2 log t, or no 3, converges to, sorry, no, this must be fast, converges to an expression which looks exactly like in the case of the branching Brownian motion, but it has a different random variable and it has a different constant. Right? And the same is true for the extremal process. We converge to a process which depends only on a and b, where we have the same form, but now we have, as I said, the m tilde t is the old m tilde t from the IID case. The pi's are atoms of the Poisson point process. Now again with a random intensity which is given by a random variable y, a, and a constant c of b. And now these deltas, they are again constructed as before, but now they are conditioned on something even less likely, than we are conditioned for the maximum of the branching Brownian motion to go like square root of t times b times t, and b is larger than 1. So it's something, so it has to go even much faster off to infinity than it really likes to do that. So it's again a process which looks more or less the same way. And the y I will show on the next transparency when we go to the proof. So how do we prove this? So we prove this in 2 steps. The first, and that was actually 2 papers. The first, that is considered a particular case where the function a has just 2 slopes, just a single time change of speed. Right? So there's a position b, so the speed goes like s times, so the a of s goes s times sigma 1 squared up to b, and then it goes off with the speed, there's a sigma 2 squared afterwards. Right? So this is just such a function. And then we have to do 3 things beyond what was known in ordinary BVM. So first we have to show that the particles localize at the moment of the time stage. So the particles which go all the way to the maximum, they're actually even much lower at the time change. They're coming from very low, from a level, they have to go through a narrow gate of which square root of t at a position square root of 2b times t times sigma 1 square, which is well below, by a constant times t below the level of the maximum. So they are, they can really pick from, these losers, basically down there. But you have to be just at the right height. Then you have to show that this martingale that appears here is not the derivative martingale. So the YA is actually this martingale, which doesn't have, in the derivative martingale there was a term here with xi minus something or other, right? Here we have something which just looks like a partition function. Actually, this martingale appeared in McKean's original paper, so we call it McKean martingale. And we have to show that this martingale is uniformly integrable, which you can, because of the sigma 1 squared is less than 1. So if sigma 1 squared is equal to 1, then this martingale is not uniformly integrable and converges to 0. And therefore, you have to go to this derivative martingale. Right, so this is one thing. And then you have to look at the asymptotics of the FKPP equations. You have to go into Bramson's book and sort of squeeze out of the estimates that you have, the estimates for the traveling for the solutions well ahead of the actual traveling wave. So you have to get the asymptotics very, very far ahead, but this can essentially also all be done. And then you get the answer for the case when A is a one-step and a piecewise constant function. And then the next step is to use, and that I like very much, to use Gaussian comparison. So for the general case of a function that lies below, what you do is you construct two-speed branching Brownian motions that have a property that at near 0 and near 1 they lie below and become very close to they have almost the same slope as the function that you are interested in, and then you show that Laplace functionals in fact are, but it's a little bit more complicated. So you show that when these are good approximations for the Laplace functionals of the other case. So you show actually that there's you have to be a bit careful in this. It's not quite so trivial, but more or less that's what you do. So it's just Gaussian comparison that kicks in, and it's Gaussian comparison not with a step function, but with linear functions. This is important. If you were to do this with step functions only, it wouldn't work. It wouldn't work. So you have to understand the BBM and to understand the general case. Now, if you are in the case above the straight line with this strictly concave situation, then of course we already know that everything has to change. Even the order of the maximum changes. The order of the maximum we know. If A is piecewise linear, so if you take a piecewise linear function, then you can again do everything by just sticking together what you know about branching Brownian motion. You just stick these BBM processes together, so that's easy and not very, it's probably useful, but it's not interesting. If f is a strictly concave function, then Frank Zeitouni and then Mayan and Zeitouni have shown that the correct rescaling is now changed. It changes, there's no longer the logarithm, but there's a power t to 1/3. T to 1/3 comes from, I know there's a slight relation to, at least to Patrick Ferrari, because it has to do with the Airy process, so there's still a relation to KPZ in some way. So this has to do with a Brownian motion avoiding a curved curve, not a straight line, but a curved one that gives you this 1/3 asymptotics. And then here's a logarithm which can, so this I can understand relatively easily. These constants can all be computed, but there's no explicit form yet there for the corresponding extremal process. So this is something I would like to do, but it looks relatively hard. But I have some ideas. Of course, what will happen in this picture, everything is really completely different from the case below. Okay, so this is roughly where we stand. Just a few words. So this, you can always say, why would you even be interested in things which are, which have a hierarchical correlation? Why are you interested in trees? Well, trees are nice to look at, like if you go in, I'm really fine. They're nice, particularly here in Buenos Aires. I saw some fantastic trees, and but of course this again there's somehow a belief that these structures extend beyond trees, and there are also some results. So, of course, one thing I didn't mention now is in the case of branching random walk, most of the results that you can get for branching Brownian motion can and have been extended to branching random walk. We started already with Bramson's 78 paper, and then there are lots of things, and the full extremal process has been obtained in 13 by Madul, and okay, so this is one thing which is relatively, well, it's usually more work here, because you don't have a nice FKPP equation at your disposal, so you have to do things with root force and heavy moment computations, but still. Then there's the Gaussian free field, which has already been mentioned here several times, and just point out that Biscoff and Louisdor, they show it exactly that, you know, part of what that the structure should be very similar to the branching Brownian motion case. They have already, you know, and that was, somebody mentioned this in this talk, so that if you look, now actually Louisdor did it in his talk, of course, and that's here that you get this Poisson part of this extremal process, but there's not yet a complete description of this decoration process. And then there are some results that are also similar at other times of random walks in 2D in particular. There's a recent paper by Belius, I'm not sure that he's still here, and Kistler, which give the corresponding precise logarithmic corrections for the maximum. And then there are things in spin glasses, etc. And there are also people who look at this in connection with zeros of the Riemann-Zeta function. So there are lots of things that are somehow vaguely or not so vaguely connected to this. So here's a list of references, and there are the pictures of my co-authors. So I think I will stop here, and thank you very much for your time.